I would like to talk today about what I think is one of the greatest adventures human beings have embarked upon, which is the quest to understand the universe and our place in it. My own interest in this subject and my passion for it began rather accidentally. I had bought a copy of this book, The Universe and Dr. Einstein, a used paperback from a second-hand bookstore in Seattle. A few years after that, in Bangalore, I was finding it hard to fall asleep one night, and I picked up this book thinking it would put me to sleep in 10 minutes. And as it happened, I read it from midnight to 5 in the morning in one shot. And I was left with this intense feeling of awe and exhilaration at the universe and our own ability to understand as much as we do. And that feeling hasn't left me yet. That feeling was the trigger for me to actually change my career from being a software engineer to become a science writer, so that I could partake in the joy of science and also the joy of communicating it to others. And that feeling also led me to a pilgrimage of sorts, to go literally to the ends of the earth, to see telescopes, detectors, instruments that people are building or have built in order to probe the cosmos in greater and greater detail. And so it took me from places like Chile, the Atacama Desert in Chile, to Siberia, to underground mines in the Japanese Alps in Northern America, all the way to Antarctica and even to the South Pole. And today I would like to share with you some images, some stories of these trips. I have been basically spending the last few years documenting the efforts of some extremely intrepid men and women who are putting literally at times their lives at stake, working in some very remote and very hostile places so that they may gather the faintest signals from the cosmos in order for us to understand this universe. And I first begin with a pie chart, and I promise this is the only pie chart in the whole presentation, but it sets up the state of our knowledge of the cosmos. All the theories in physics that we have today properly explain what is called normal matter, the stuff that we are all made of, and that's 4% of the universe. Astronomers and cosmologists and physicists think that there is something called dark matter in the universe, which makes up 23% of the universe, and something called dark energy, which permeates the fabric of space-time, that makes up another 73%. So if you look at this pie chart, 96% of the universe at this point in our exploration of it is unknown or not well understood. And most of the experiments, telescopes that I went to see are in some way addressing this question, these two twin mysteries of dark matter and dark energy. I will take you first to an underground mine in northern Minnesota where people are looking for something called dark matter. And the idea here is that they're looking for the sign of a dark matter particle hitting one of their detectors. And the reason why they have to go underground is that if you did this experiment on the surface of the Earth, the same experiment would be swamped by signals that would be created by things like cosmic rays, ambient radioactivity. Even our own bodies, you might not believe it, but even our own bodies are radioactive enough to disturb this experiment. So they go deep inside mines to find a kind of environmental silence that will allow them to hear the ping of a dark matter particle hitting their detector. And I went to see one of these experiments, and this is actually, you can barely see it, and the reason for that is it's entirely dark in there. This is a cavern that was left behind by the miners who left this mine in 1960, and physicists came and started using it sometime in the 1980s. And the miners in the early part of the last century worked literally in candlelight. And today, you would see this inside the mine, half a mile underground. This is one of the largest underground labs in the world. And among other things, they're looking for dark matter. There is another way to search for dark matter, which is indirectly. If dark matter exists in our universe, in our galaxy, then these particles should be smashing together and producing other particles that we know about, one of them being neutrinos. And neutrinos you can detect by the signature they leave when they hit water molecules. When a neutrino hits a water molecule, it emits a kind of blue light, a flash of blue light, and by looking for this blue light, you can essentially understand something about the neutrino and then indirectly something about the dark matter that might have created this neutrino. But you need very, very large volumes of water in order to do this. You need something like tens of megatons of water, almost a gigaton of water, in order to have any chance of catching this neutrino. And where in the world would you find such water? Well, the Russians have a tank in their own backyard. This is Lake Baikal. It is the largest lake in the world. It's 800 kilometers long. It's about 40 to 50 kilometers wide in most places, and 1 to 2 kilometers deep. And what the Russians are doing is they're building these detectors and immersing them about a kilometer beneath the surface of the lake so that they can watch for these flashes of blue light. And this is a scene that greeted me when I landed there. This is Lake Baikal in the peak of the Siberian winter. The lake is entirely frozen, and those line of black dots that you see in the background, that's the ice camp where the physicists are working. The reason why they have to work in winter is because they don't have the money to work in summer and spring, which if they did that, they would need ships and submersibles to do their work. So they wait until winter, the lake is completely frozen over, and they use this meter-thick ice as a platform on which to establish their ice camp and do their work. So this is the Russians working on the ice in the peak of the Siberian winter. They have to drill holes in the ice, dive down into the water, cold water, to get hold of the instrument, bring it up, do any repairs and maintenance that they need to do, put it back and get out before the ice melts, because that phase of solid ice lasts for 2 months. And it's full of cracks, and you have to imagine there's an entire sea-like lake underneath moving. I still don't understand this one Russian man working in his bare-chested, but that tells you how hard he was working. And these people, a handful of people, have been working for 20 years, looking for particles that may or may not exist. And they have dedicated their lives to it. And just to give you an idea, they have spent 20 million over 20 years of it's very harsh conditions. They work on a shoestring budget. The toilets there are literally holes in the ground covered with a wooden shack. And it's that basic, but they do this every year. From Siberia to the Atacama Desert in Chile to see something called the Very Large Telescope. The Very Large Telescope is one of these things that astronomers do. They name their telescopes rather unimaginatively. I can tell you for a fact that the next one that they're planning is called the Extremely Large Telescope. Right? And you wouldn't believe it, but the one after that is going to be called the Overwhelmingly Large Telescope. But nonetheless, it's an extraordinary piece of engineering. These are 4 8.2 meter telescopes, and these telescopes, among other things, they're being used to study how the expansion of the universe is changing with time. And the more you understand that, the better you would understand what this dark energy that the universe is made of is all about. And one piece of engineering that I want to leave you with as regards this telescope is the mirror. Each mirror, there are 4 of them, is made of a single piece of glass, a monolithic piece of high-tech ceramic that has been ground down and polished to such accuracy that the only way to understand what that is imagine a city like Paris with all its buildings and the Eiffel Tower. If you grind down Paris to that kind of accuracy, you would be left with bumps that are 1 millimeter high. And that's the kind of polishing that these mirrors have endured. And extraordinary set of telescopes. Here's another view of the same. The reason why you have to build these telescopes in places like the Atacama Desert is because of the high altitude desert. The dry air is really good for telescopes, and also the cloud cover is below the summit of these mountains so that the telescopes have about 300 days of clear skies. Finally, I want to take you to Antarctica. I want to spend most of my time on this part of the world. This is cosmology's final frontier. Some of the most amazing experiments, some of the most extreme experiments are being done in Antarctica. I was there to view something called a long-duration balloon flight, which basically takes telescopes and instruments all the way to the upper atmosphere, the upper stratosphere, 40 kilometers up, and that's where they do their experiments, and then the balloon, the payload is brought down. So this is us landing on the Ross Ice Shelf in Antarctica. That's an American C-17 cargo plane that flew us from New Zealand to McMurdo in Antarctica. And here we are about to board our bus, and I don't know if you can read the lettering, but it says Ivan the Terrabus. That's taking us to McMurdo, and this is the scene that greets you in McMurdo. And you barely might be able to make out this hut here. This hut was built by Robert Falcon Scott and his men, when they first came to Antarctica on their first expedition to go to the South Pole, because it's so cold, the entire contents of that hut is still as they left it, with the remnants of the last meal they cooked still there. It's an extraordinary place. This is McMurdo itself. About 1,000 people work here in summer and about 200 in winter when it's completely dark for 6 months. I was here to see the launch of this particular type of instrument. This is a cosmic ray experiment that is being launched all the way to the upper stratosphere to an altitude of 40 kilometers. What I want you to imagine is this is 2 tons in weight. So you're using a balloon to carry something that is 2 tons all the way to an altitude of 40 kilometers. And the engineers, the technicians, the physicists have all got to assemble on the Ross Ice Shelf, because Antarctica is, I won't go into the reasons why, but it's one of the most favorable places for doing these balloon launches, except for the weather. The weather, as you can imagine, this is summer, and you're standing on 200 feet of ice, and there's a volcano behind, which has glaciers at the very top. And what they have to do is they have to assemble the entire balloon, fabric, parachute, and everything on the ice, and then fill it up with helium, and that process takes about 2 hours. And the weather can change as they're putting together this whole assembly. For instance, here they're laying down the balloon fabric behind, which is eventually going to be filled up with helium. Those 2 trucks you see at the very end carry 12 tanks each of compressed helium. Now, in case the weather changes before the launch, they have to actually pack everything back up into their boxes and take it out back to McMurdo Station. And this particular balloon, because it has to launch 2 tons of weight, is an extremely huge balloon. The fabric alone weighs 2 tons. In order to minimize the weight, it's very thin. It's as thin as a sandwich wrapper. And if they have to pack it back, they have to put it into boxes and stamp on it so that it fits into the box again. Except when they did it first, it would have been done in Texas. Here, they can't do it with the kind of shoes they're wearing, so they have to take their shoes off, get barefoot into the boxes in this cold and do that kind of work. That's the kind of dedication these people have. Here's the balloon being filled up with helium, and you can see it's a gorgeous sight. Here's the scene that shows you the balloon and the payload end to end. So the balloon is being filled up with helium on the left-hand side, and the fabric actually runs all the way till the middle, where there's a piece of electronics and explosives being connected to a parachute, and then the parachute is then connected to the payload. And remember, all this wiring is being done by people in extreme cold, in sub-zero temperatures. They're wearing about 15 kilograms of clothing and stuff, but they have to take their gloves off in order to do that. And I would like to share with you a launch.
Okay, release the balloon, release the balloon, release the balloon.
And I'll finally like to leave you with 2 images. This is an observatory in the Himalayas in Ladakh in India, and the thing I want you to look at here is the telescope on the right-hand side, and on the far left there is a 400-year-old Buddhist monastery. This is a close-up of the Buddhist monastery, and I was struck by the juxtaposition of these 2 enormous disciplines that humanity has. One is exploring the cosmos on the outside, and the other one is exploring our interior being, and both require silence of some sort. And what struck me was every place that I went to see these telescopes, the astronomers and cosmologists are in search of a certain kind of silence, whether it's silence from radio pollution or light pollution or whatever. And it was very obvious that if we destroy these silent places on Earth, we will be stuck on a planet without the ability to look outwards, because we will not be able to understand the signals that come from outer space. Thank you.